Hello students, we are going to talk about equilibrium today. So the first thing is reversible reaction. This is a chemical reaction in which products can react to form the reactants. And so it does use a double arrow for the reaction. So in this reaction you have your reactants on the left and your products on the right. And when we talk about this, the forward reaction is going from reactants to the products, but the products can then also reform the reactants, and so that would be the backward reaction. And then at some point, the reaction should reach equilibrium. So at some point they'll reach equilibrium, and that's when the forward and reverse rates for a chemical reaction are equal, and the concentrations of the reactants and products do not change. This says two things: when the forward and reverse rates for a chemical reaction are equal. So if you're looking at this, if you're this is the rate versus time, so the forward rate, it's sloping downwards, so it has a negative slope, and so that forward rate is decreasing, and then that reverse rate is increasing, and then at one point they'll become equal, and we've reached equilibrium. So at this point, we've reached equilibrium. I'm actually going to delete this part, and I'm going to highlight this area. So this part right here would be your equilibrium. And then the second part says the concentration of the reactants and products do not change. So this says amount. Sometimes it might say concentration, like on the ones down there, right here in these graphs. But at the point where the slopes stop changing, so the reactants are decreasing in amount, the products are increasing in amount in this graph. So at this point about right there is when the slope gets to zero in both. This, once again, is when we have equilibrium. So the equilibrium constant . The equilibrium constant is a constant that relates the concentrations of products to reactants, and they help determine if a forward reaction or a reverse reaction is favored at a specific temp. So for the general equation, your A and the B are your products, the N and the M are your coefficients. So your N, M, X, and Y are your coefficients. A and B are your reactants, C and D are your products. And so you're going to take the concentration of C and put it to the power of its coefficient times the concentration of D, put it to the power of its coefficient, divide by the concentration of A to its power of coefficient, and divide by the concentration of B to the power of its coefficient. The brackets means concentration, molarity. Note, only aqueous and gas substances are included in the above equilibrium system. Solids and liquids are assumed to be 1 for their concentration, so they're not in this expression. So how do you know what is favored? If KEQ is more than 1, the forward reaction is favored, and there will be more products at equilibrium. If KEQ is less than 1, the reverse reaction is favored, and there will be more reactants at equilibrium. If KEQ is equal to 1, both the forward and the reverse reactions are equal, and there will be equal amounts of products and reactants. Okay, we are going to draw a line on each graph when equilibrium has occurred. In addition, determine if KEQ is more than 1, less than 1, or equal to the 1. So when the slope becomes 0 for each, that's when equilibrium has occurred. So I would say this one's a little bit hard to tell, but I'm gonna say about here. If yours was a little bit off of mine, that's fine. We have way more reactants because it's higher up on the graph than products. So since there's more reactants, your KEQ will be less than 1. Okay, about when the lines go completely horizontal, so I'm going to say right about there. This time we have more products than your reactants, so your K will be more than 1. And when they get to horizontal, so right about there, and they're pretty much on top of each other, so I'm going to say KQ, I'm going to say about equal to 1, because they're pretty much on top of each other. Okay, one more example. We're going to write the KEQ expression for the reaction above. We're starting with that. So our KEQ expression, we're going to take our product, that goes on top. So NH3, make sure you have your subscripts and everything. That goes in brackets, and then the coefficient 2 becomes its power. Then we're going to take our reactants and put them on the bottoms. We have N2, and then we have H2. This doesn't have a coefficient, so we don't need to put the power by anything. We have H2, and then the power is 3. Now we're going to use the values below at the concentrations of each substance at equilibrium. Determine the value of the equilibrium constant. Okay, so we just need to take these numbers and put them into that expression. So our KQ, our NH3 value is 0.62, and we need to square that. Our N2 value is 0.45, and our H2 value is 0.14, and that needs to be cubed. I would recommend you doing the top and then doing the bottom. So 0.62 squared is 0.3844. Do not round here though, as best you can. Then I would take 0.14 and cube it and times that by 0.45, and I get 0.001238, and then take the top number and divide by the bottom number. And I get 311. Because your K is more than 1, the forward reaction is favored. And more products at equilibrium. To justify your answer, this is all you need.